All right, so welcome to our lecture on stellar distances. And so with this little lecture, we're going to be talking about all of the different ways that we measure distances within our solar system, within the Milky Way galaxy, and beyond. So within the closest part of our solar system, within the inner planets, radar is the kind of the easiest way for us to measure distances. And really and truly all that is bouncing light off of those other objects. We also use radar to do detailed work on imaging items, especially for planets like Venus. So we've talked about Venus in the past, very thick atmosphere, cannot see the surface. We have landed probes on the surface of Venus, so the Venera mission was down there and able to send back photographs from the surface. But in general, we didn't really know what the surface looked like. But we were able to use different telescopes to bounce light off the surface of the planet, and then by measuring how long it took that light to get to the surface and back again, those little changes in the times helped us figure out high points versus low points. So it did allow us to do to kind of get a look at the surface of Venus, even though we couldn't see it. So again, using technology to help us work with light that we cannot see in order to kind of clear some of our blind spots that we have in astronomy. So once we were able to get precise measurements on distances between us and Mars, us and Venus, and Mercury, and the Moon, it helped us get those distances as precise as possible, and then we were able to figure out all of the other distances around us just based on Kepler's law. So once we get to the point where radar does not work anymore, it's just too far, because remember, we've got to get that light has to go all the way out to the object and then turn around and come back. And light does follow that inverse square law, so you do tend to have a reduction of the amount of energy you're sending out and back. So the other way we can look at it for things that are still fairly close to us, like nearby stars, is parallax. And we started talking about parallax very, very early in the course. And it was, the Greeks understood parallax, and they understand how to triangulate on the Earth. And so then we're having a very hard time understanding how you could have distances in space where that you would actually be able to see the stars move. And because we didn't see the stars move, therefore, the Earth could not be going around the sun. So that was one of the huge arguments that was keeping the Earth stationary. So again, here is our little model. We have the sun here in the middle, and we have the Earth orbit going around. Then we have two views, the B view from Earth's position on this side of the sun, and the A view from the position on this side of the sun. And we're trying to calculate the distance to this red star, and we're using the background stars, so we're making that assumption that there's three-dimensional space, and by looking at the difference between our A view and our B view, then can measure the angle of that change. So knowing that we have this baseline here as one astronomical unit, that kind of gives you the base of this triangle and then the angle that is observed. So then your distance formula is just 1 over what that angle is. We measure the angle in, it's a measurement in the sky, so remember that's in arc seconds. And then we also have a very special word and measurement for the distance, where the angle that is created here is exactly 1 second of arc. And when you have that, then this distance right here is what we call a parsec, right? So you've probably actually heard that before. It's a 1 arc second of parallax. And so 1 parsec just happens to be 3.26 light years. All right, so we can use parallax then to measure stars that are a little bit closer to us, where we have definite background stars much, much further away, so we can see that that artificial motion in the sky based on our rotation around the sun. So here are some of the stars that we can actually measure with parallax. So this is a nice little view of our local stellar neighborhood. So our sun is here in the center as a point of reference. It's our reference since we're moving and measuring away from the sun. And this is three-dimensional, so the lines just show where they belong on the graph, but the points of light, these little red dots and gold dots, are the actual three-dimensional positions of those stars. And again, here's our scale, and that's 10 light years. So right here together on this closest ring is Proxima and Alpha Centauri, which are our closest neighbors. So two space missions, because it's easier to do all of these measurements in space, because then you can receive more light from distant stars. Were done by the Hipparcos and the Gaia mapping missions. And so the points that you see here are groups of stars and the numbers of stars. So the redder the dots, the more stars there are in that cluster. So these don't represent individual stars, they represent groups of stars. And so then if you remember our spectrum, we have our cool M stars on this side and our hotter O stars here, and then luminosity increases as you go up the scale. So the plot here is showing this main sequence of stars and then this branching off into our giants and our supergiant stars. So these all have measurements that have an accuracy of 10% or better. And so kind of coming back into the spectral types and back into our HR diagram kind of helps us move on to kind of our next little step of measurement, our next different type of measurement. When you're looking at the spectral types in the HR diagram and the types of stars that we have to measure against both in the galaxy and in other galaxies as well, the abundances, the numbers of the different types of stars are often quite surprising. So if you look at our sun, right, so about 3.5% of all of the stars that we know of are stars like our sun. And when you start looking at the really, really large stars, the number starts decreasing as you get to those larger and hotter stars. And then the number starts increasing as you get to those cooler stars. Now that shouldn't be quite surprising, right? So we talked a little bit about kind of the life cycle of stars just briefly. We haven't gotten into the actual births and deaths of stars. But remember, these cooler stars are living longer, right? So you should expect to see more of them out there, where these guys have already fallen off the main sequence and are dying more rapidly. And so we would see some of those numbers translated into the white dwarfs. So these white dwarfs are the remnants of other stars that have already died. All right, and so then also supernova remnants and all of those types of things would be an accounting of where these guys have gone. All right, so our next step. So now we kind of have an idea of the abundances of stars that we have in our solar system. Most stars have some sort of variability to them. They change in the amount of light that we actually see, and some of this can be caused because they're binary or multiple star systems, so they're blocking each other's light on a regular basis. Some of them can be because they are aging and dying, and so the dynamics, that hydrostatic pressure is changing. But there are some stars that are just inherently variable. They have very, very predictable patterns. And so Henrietta Leavitt, who is the woman who's standing here on the right in the dark dress, after studying thousands of stars in the Magellanic Cloud, discovered that many, many, many of these stars were variable stars. And after years of trying to find a pattern of what that was eventually able to see that there was a pattern, and that the brighter that the star was, that these variable stars were, if they were very, very bright, then their period of variation was going to be very, very long. And we call them Cepheid variables because they were named after the star Delta Cephei. So that is one of the stars in the constellation Cepheus the king, and we'll have to add a star map to our module so I can show you where that is. But that was one of the stars that was that way, and so it was kind of all the stars were kind of grouped using that name. So Henrietta Leavitt here in the right in the dark, and then this is Annie Jump Cannon. And so if you remember, Annie Jump Cannon we talked briefly about was the one that actually rearranged the stars and took a look at all of the star spectra based on temperature and looked at the spectra lines and looked at where things were being ionized to understand how hot those stars were, and reorganized and put the stars into our current system. Oh, be a fine girl, kiss me. So here is a light graph, and so here is one of the variable stars. And this is what you would expect to see. So you would see an increase of the magnitude, and then a slow decrease over time, and then a rapid increase, and a slow decrease. And Cepheid variables, they nicknamed this wave the shark fin, because you would see that very rapid increase and slow decrease over time. And so you were able to judge the period from crest to crest. And so if you knew that this particular period was supposed to go with a particular brightness of star, and you measured the brightness and it was less than what you were expecting, then there was two possibilities. One, there was something between you and the star, or that star was very, very far away. And so by looking at other stars around it, you could determine if there was something in your way. But those Cepheid variables were key to measuring things much further away, because if our galaxy had Cepheid variables and the Large Magellanic Cloud is just another galaxy that we're consuming, then other galaxies should have Cepheid variables as well, and they should follow the same pattern. So it was kind of one of these aha moments, and we make it sound very simple, but it did take quite some time to get and understand what that pattern actually was. And at the time, the computers, the Harvard computers, of which Henrietta Leavitt and Annie Jump Cannon were members of, they were processors, they were calculators. They never got to use the telescopes themselves, they never got to direct the research themselves, they just ended up with the data. And so they were able to find this period luminosity relationship, brighter stars, longer periods, and they identified two particular groups, the Cepheid variables, for which are going to end up being very, very useful, but another group of RR Lyra. So from the constellation Lyra, that one of those stars became kind of the namesake of those particular types of variable stars. But you can see they have very different characteristics, so mixing them up would not be a good thing. All right, so here is the cluster again of the RR Lyra stars. And so the reason why I wanted to point out that confusing them would not be great is because they had been confused from time to time. People using these variable stars, trying to use those periods and the luminosity to create distances, and by using the wrong formula with the right star, or other way around, you could end up with really bad measurements. And we're going to look at a debate here where that happened. So, great debate. So, remember, at this point in time in 1920, the Milky Way galaxy was the universe, right? It was everything that we could see. The Andromeda galaxy is a naked eye object, and during this time period, it was just a nebula, right? It was just another cloud of gas and dust in the sky, but all within the Milky Way galaxy. And for many, the sun, of course, was close to the center of our galaxy, because that's what we tend to do, is put ourselves in the center. So during this great debate, it was called that because we were basically establishing what is the universe. Is it the Milky Way galaxy, or is it something greater than that? So Shapley's argument was, so these are both astronomers, both observational astronomers, very, very different in their personalities, but Shapley's argument was that the universe is our galaxy. So everything that we see is within our galaxies, but it's a very large galaxy. So it's 100,000 parsecs across. But the sun in our solar system is nowhere near the middle. We're off on the edge of this galaxy. But all the things that we can see, all of these nebula, are actually part of the Milky Way galaxy. So everything is encompassed in what we can see. Curtis's argument was a little bit different. So he was of the firm belief that things like that nebula that we see near Andromeda, those spiral nebulae, those were other distant galaxies. They were completely separate from the Milky Way galaxy, and they must have been, very, very large and very far away. But that our galaxy wasn't really that large. It was only 10,000 parsecs across. But that the universe would have been made up of many, 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 many different galaxies kind of independently in little islands all on their own. So the debate went on and it was not completely resolved. If you were to go and base the actual argument itself on your high school debate team kind of type of criteria, Curtis probably was the one that won the debate, but they didn't have any reliable measurements. Shapley was using our Lyra variables to try and make those measurements, which is why things didn't work out. But we also did not have really good ways to do these long distance measurements. However, a few years after that, and this happens all the time in astronomy, you say, here, if we had this and could measure that, we would know the results. My theory is that the Andromeda Nebula is actually a galaxy far, far away, but I can't prove it. But if someone comes up with this method, right, of using Cepheid variables then and finding one there, then you should be able to prove me right. So in 1926, Edwin Hubble was able to identify in the Andromeda Nebula Cepheid variables. And by using the period luminosity law that Henrietta Leavitt created, was able to create and calculate the distances to the Andromeda Galaxy, and that distance was so great it had to be outside of our own galaxy. The other thing that happened shortly after that is figuring out that interstellar absorption, so all of this material that is in space, does change the way that we see light, and also that globular clusters, how they're distributed and how they orbit within the Milky Way galaxy, all helped better define the size of our galaxy. So in that way, Shapley was more correct in the size of the galaxy, and that where we were located in the galaxy, because we could see that from the distribution and the way the globular clusters were orbiting the center, and we were not in that point. We were not in that privileged point of seeing the globular clusters orbiting us. They were orbiting someplace else. But Curtis was much more correct on the fact that all of these spiral nebulae were much, much further away, and indeed these island universes all on their own. So here's an image of Edwin Hubble and the Hooker telescope, and putting Henrietta Leavitt's theory into practice. And this cracks me up a little bit, because anytime you ask kids, draw me a picture of an astronomer, it almost looks like this. You have an older white guy, normally in a lab coat with a pipe in their mouth, with their eye, glued to an eyepiece of these ginormous telescopes. And of course, there we go, Edwin Hubble. So just kind of perpetuating that odd vision of what an astronomer is. All right, so galactic measurements. So one thing, and they point this out in your book very well. In fact, I just brought that in because it's a very good statement. We're going through all this material very quickly, and we're not necessarily sharing with you all of the agony of each step that people had to go through to actually take their hypotheses, take their observations, and work through them and test them, and have multiple people test them until they could create a formula, create a law, create a theory. So you don't get to see necessarily all the messy stuff. We kind of jump you straight to the, and then here's what happened and it worked out. But to be fair, a lot of the measurements to different objects were not necessarily super precise. That was one of the wonderful things about having Hipparchus and Gaia out in space away from the Earth, making those measurements and getting those percentages lower, down to about a 10%. And if you imagine, that's fine when you're sitting here and you're just talking about distances between one thing and another, but if you were planning a trip someplace and we were screwing up distances up to 25% or more, you would get stuck halfway between Earth and whatever your objective is, and in a spacecraft without any fuel left, and that definitely would not be very acceptable. All right, so here's kind of a really quick review of the measurement steps we have so far, and we will continue this conversation as we get into galaxies and taking a look at galaxy formations and the expansion of our universe. So right here in the center, here's our Milky Way galaxy. It's actually a barred spiral, but we're out here, out in the spiral arms. We're on a spur of a spiral arm. Here's our little sun. This is not to scale. And so what we have here really is Earth, and we've got this little diameter here that's going to represent what we can do in radar. With the original parallax, we have this. With our new parallax limits, thanks to our space telescopes, we can measure stars out to this limit. Then after that, we're jumping into Cepheid variables, and then we'll get into these other types of variables as we get further along in the course. So kind of our different distance ladders. So some of the words that you'll hear repeated in other places is a distance ladder. It's the different steps that you take to measure distances further and further away. And then objects like Cepheid variables being standard candles. And what they mean by that is an object where you know what the luminosity is and can therefore judge the distance. And so just as a really quick reminder, here are some of the distance ranges that you have for parallax, for using variables, our Lyra variable stars, and being able to use Cepheid variables, for example. All right, so that is our little distance unit. So go back into the module and check to see what activities follow this, and then we'll catch up with you on the next little lecture.